Hello, my name is Jake Seifert. I'm a PhD student at Penn State working with my advisor, Dr. Herschel Pangborn. This presentation focuses on our work with collaborators at Purdue University and the University of Texas, Dallas, titled Successor Sets of Discrete-time Nonlinear Systems Using Hybrid Zonotopes, and was presented at a rapid interaction session at ACC 2023 in San Diego, California. In a single sentence, the main result of our work is that hybrid zonotopes enable verification of nonlinear systems. Here we have an example of a 2D nonlinear system with a linear feedback controller that saturates. For this example, the goal is to verify satisfaction of the state constraints. For a single initial condition, one could simulate a trajectory, but let us consider the problem of trying to verify a set of initial conditions. Sampling the set of initial conditions can give some insight, but it may require a large number of simulations to gain confidence. Furthermore, the process of sampling trajectories becomes computationally prohibitive in higher dimensions. Set propagation techniques seek to generate sets containing all possible trajectories, and our set propagation technique is novel in two main ways. The first is that we seek to represent functions for the controllers and the dynamics as sets, and the second is that we use a set representation called the hybrid zonotope. This allows reachable sets to be generated with a time complexity that scales linearly with dimension and with memory complexity that grows linearly with time. Our follow-up paper builds on the numerical results and can handle continuous time dynamics, in this case a pendulum, and a neural net trained to approximate a nonlinear model predictive controller. So I will now pen my summarizing statement to read that hybrid zonotopes enable verification of nonlinear systems in closed loop with advanced controllers. We handle this more challenging example using the same approach. Again, we represent the feedback control law and the nonlinear dynamics using the hybrid zonotope set representation, which enables efficient and scalable computation of reachable sets. I'd like to draw attention to three key ideas used in our approach. The first is the hybrid zonotope set representation. What sets the hybrid zonotope apart is that they leverage binary factors, which allows for the efficient representation of non-convex sets. The second is that existing piecewise affine functions, such as special ordered sets, and neural nets using ReLU activation functions can be efficiently converted into or represented as a hybrid zonotope. The third key concept is functional decomposition, and here I show the function cosine of sine of x and how it can be broken apart into simpler base functions, cosine and sine, in a higher dimensional space. This idea can also be used to decompose multivariate nonlinear functions into unary and binary functions with 1 and 2 inputs respectively. This is powerful because it allows for approximations of the system dynamics in many dimensions to be generated while only ever having to sample a 1D or 2D space. If you would like to learn more about how hybrid zonotopes enable verification of nonlinear systems in closed loop with advanced controllers, and for our other work on reachability analysis and state estimation using hybrid zonotopes, the QR link directs you to the PAC Lab website, where you can also find contact information for Professor Pangborn and myself. We hope to hear from you, and thank you for listening.